This is an online presentation for the APSEC Asia Pacific Software Engineering Conference about multi-factor approach for flaky test detection and automated root cause analysis. And my name is Azim Ahmed. I'm the presenter, and we have done this work with Francisco, Hishang, and Christian Sandal, Ula Liefler in Linköping University and with Chalmers University of Gothenburg, Sweden. Um, the outline of this presentation is about we'll present I will present some introduction about what flaky test is, why it matters, why it requires practitioners and researchers attention, related work, a little something about what we have done before and the inspiration for this work, and the MD Flaker, the tool and the technique we are presenting in this paper. We will talk about results, discussion, conclusion, and then some question answer if you have at the end. Flaky test. What is flaky test? It is gaining a lot of attention. If you go and search something on Google Scholar, you will find that many people, many researchers are investigating this area. And we are working in a software center where many companies come together and discuss their issues. And we have seen that it flaky test annoys many people. It is about a test that changes its outcome without any modification in the code base. For example, you run your test cases and everything was fine yesterday, and then you came back and you ran all the test cases again without any modification in a code base, and then you see 5 test cases are failing or 10 test cases are failing. If you look at Google or other statistic, I have mentioned a paper, sometimes 5 or 10% of their test cases are flaky. So now you wonder, okay, what's happening? Why they are failing? Everything was fine yesterday. Now 5 test cases failing, and you have to dig deep. You haven't changed anything, and then you spend a lot of time to find out why the test cases are flaky, and there are many different reasons. So they are also called non-deterministic tests, and we want to address those flaky tests in that case. Usually, what people do when they find that 5 test cases are failing today, everything was fine, they rerun them. Sometimes they rerun them 100 times or 200 times to make sure are they passing in those 100 times, or are they still failing between 100 times, passing and failing. So if they are passing again 100 times, they ignore those 5 failure which they observed today. If they are passing and failing, then they dig deep why it is happening. So most of the common solution for flaky test is to rerun. It is costly. Let me bring the pen so I can. It is it is costly, of course. It consumes a lot of computing power when you have to rerun 100 times. Imagine your test case take 5 minutes or 2 minutes, or some companies have test cases that are running 10 minutes. So rerunning them 100 times will consume a lot of power. Of course, it shares your testing budget. You have a budget that you have to spend on a testing. If you have to rerun them after every build or after every week, it's going to share that budget too, and it's unreliable. For example, you don't know, should you rerun them 100 times, should you rerun them 200 times? So there is no real number that you can follow. Maybe it finds it's fine with 100 runs, but it does not reaches to those circumstances or condition when it becomes failed the first time. So you don't know that. And mostly they are the post build solution. Okay, once you run it, once you find that the test case is failing, then you find you have to rerun them after it is failing. So there is no pre-solution. What we are talking about, we have observed that it is a multifaceted problem. It's not a one thing. There are many factors that influences test flakiness. It could be a test case code, the way you have written it, what you have written it. It could be a source or production code, the system under test. So then it's not a test flakiness, it is a source code flakiness. It could be test infrastructure, the infrastructure you have built around your testing activities, that's flaky. For example, Jenkins or the CI tool chain you are using. It should be something outside the company. For example, some sub libraries that you are using, they are not available or they are flaky. They don't do the deterministic behavior. Or it could be individual people who are writing test cases. So there could be different things that are affecting flaky test. In our previous work that we have done in the Linköping University, we have find the practitioners' perception of test flakiness. What do they think affect test flakiness? And then we found some factors that I will explain in the later slide. We did this study with 5 different companies in Scandinavia, and then we find out what the practitioners feel. We also use machine learning algorithm to find out whether the test case is flaky or not. So it's predict similarly to a spam or non-spam email scenario. Um, um, in the previous work, we have identified many factors that different companies A, B, C, D find out in their observation, in their perception that they makes a difference. For example, test case simplicity, test case size, test case age, how robust it is, and test case smelliness. And then they have something related to system under test. But this is the other paper. We're not talking about that today. But after this paper, after this research, we find out that yes, there are factors that make that influence the flaky test. So why don't we use a multi-factor approach using these factors? We also have seen that the test case size has an effect on a flaky test or a non-flaky test. So you can see that the non-flaky test has a less number of lines as compared to a flaky test. But this is the other paper again. We have a evidence, stronger evidence that different factors have a different influence on the factor. So we have used test smells in this paper as one factor. Flaky frequency, for example, history of the test case. How often does it become flaky? How often does it fail when no changes have been introduced? Test size, how many number of lines are uncommented lines are in the, and the test back coverage, that is our technique. That is a novel, no, not a novel, a modified technique and a big contribution of this paper. Test smell, as you all know, it is a bad design, like thread.sleep. You write thread.sleep, you try to access a file without checking if it exists or not. So these are the things contribute as a test smell, and different test smell correspond to a different type of flakiness. This is the evidence that it makes a difference when it comes to test flakiness. Flaky frequency, history of each test case, whether the test outcome changes without any modification. So we keep an eye on an individual test case, and if it is more likely to flaky, we use that value. And then we have a test case size, how many number of lines these test cases have. And we use all these factors, and we use a KNN algorithm, in a machine learning algorithm, to decide, depending on the values of these factors, whether this test case is flaky or not. And then comes this traceback coverage that we said is a unique contribution of this paper. It's a modified approach of the differential coverage proposed by Jonathan in the 9, this paper. So they have used this differential coverage. The idea is that when the test case fail and it does not execute the changes, a code changes, then it is more likely to be flaky. For example, you change file C1 and the test case T20 is failing, which has nothing to do with the C1, then it is more flaky. We use the same technique, but we have optimized it. For example, in the differential coverage, the author have used test code instrumentation. They have injected something to find out what has been changed. And they do not use fail test case, they use all the test case. But our technique, which is the traceback coverage, it does not instrument anything. It is like a black box technique, and it only works on a failed test case, because if some test cases are already passing, you don't need to worry about it. It's only the failed test case that you want to see, is it a real failure or is it a flaky failure. And then we have a method. We unfortunately we are only working on a method level, because in the traceback we can see which method fails in a test case. We don't go for which line, because we find it hard to find what lines have been changed in a source code. So we just work on a method level. For example, here you can see that the test load birth name fail. It calls another method load birth name, and that calls another function load data. And in the load data, you have that the file name is birthnames.py. So that's how from the test case to source code we can see what has been changing. And then if this is the log file, and we are getting this information from the log file, and then we get some information from the GitHub where things have been changed, and then we find intersection if they overlap, what method have been failed and what method have been changed. If they are same, then the test case is not flaky. If what have been changed on the both side are have a difference, then it is more likely flaky. For example, here we say that you use a source code for a test smell, you use a modification for a test peak coverage and flaky frequency, and then you take all these factors and you put them in a DDB, and then you evaluate on a KNN model which we have already trained, and then it predicts whether the failure test case is flaky or not flaky. So the research question we are answering here is, to what extent do the chosen factor, which is test smell, flaky frequency, test size, or traceback coverage, reveal test flakiness? So we are combining each factor and taking a single factor and finding whether the predicted test case is correct or not in terms of accuracy, precision, and false positive and false negative. What are the more effective combinations we can have? What type of information can MD Flaker reveal to developer to help understand the root causes? That is the second part. Not only factor, we want to know whether the information our technique is providing, does it answer the question why this test case is flaky? Not only whether it is flaky or not, but also why it is flaky. So we have seen that yes, the combination of the traceback with any of the other factor reveal a good accuracy, around more than 80%, 80, 83, 82. If you look at here, we have used traceback, size, and frequency. They still reveal 84, 83, 82. Traceback, all the factors, they reveal 85. I still say it is more than all the previous combination of the factor. If we use a single factor like frequency, it's only 72. The size only 64%. Smell 55. Traceback itself is a strong technique that we say it's 83%. So we have seen that when you combine different factors, particularly traceback, it reveals more accuracy. I won't go in detail into the precision and recall, but due to the limited time. So we can see that yes, the combination of the factor and the factor that we have chosen makes a difference. So we have seen that yes, the finding in the paper is that it combining all factor often yields high precision, accuracy, and recall between 0.78 to 0.98. However, since different combination yields different result, we can see that okay, which factor have a more importance, and we can see that traceback and frequency, they complement each other in that case. Size is not a reliable predictor. We don't believe in this, but I think more investigation might be needed to find out about the size. Now there is this question too, that what information does it reveal that can help the tester? So we can see it can tell you that okay, if you can talk about test smells, you can take a reporting mechanism on each of the factor: test case size, smell, traceback. So I'm showing them some of the reporting of the test case smell. You can see that 95% are without smell. For example, thread.sleep or input output or checking the file. We have used the IO, network, randomness, training, these type of test smell. So it tells you how many number of smells are there. IO are 2 test smells, more are 24 number of smells are in network. You can also see where these test smells are. For example, in the test case, this number of smells are 6, the type is network, URL, and the line number this, path is this. So this details some information. So let's say test case 1 is flaky. You can go and you can check the test case and you look into the file number. Okay, this is flaky because of this. So it does help. It also tells you what is the number of lines in each test case, what is the size. You can see that 13 of your test cases have more than 70 lines. So you can look into it. So what did we learn? That we need an automated root cause analysis. People are not interested now that whether the test case is flaky or not. In a flag, they want to know why it is flaky. They want to have some indication so they can dig deep rather than spending 3 days to find out it is the reason. So they want some indications. Precision depend on a data set. We find out that it's more depend what type of system is under test. If it is a machine learning component, of course it's more undeterministic because it's a machine learning component. There's more randomness nature in it. So you can say that the traditional system and other system, they are all same. You need to look into it. Flakiness into a production code, we need to see. Uh, we are talking about only a test case code. People need to investigate flakiness in a production code, in a source code. And we have to investigate specific category: input, output, concurrency, order dependency, network, randomness. Each specific category should be explored in terms of flakiness. So we also have a comparison, but we won't go into detail because of the time. You can have a look on it, how our technique is it's different as compared to other techniques. And the conclusion is that yes, different factors have an influence. It's important to consider that factor. It could be testing infrastructure. It could be outside library. So you need to find those factors that have effect um, in your setting. And we need to work with why now should work should be done, why the test case is flaky. So more of an automated root cause analysis and specific investigation, specific direction. I think rather than having a survey with all the possible known factors, we should take one factor, which could be size, which could be smell, which could be input output, which could be randomness, which could be network, and we investigate how can we reduce test flake in a specific category. And we should also look into flakiness in a production code or flakiness into a testing infrastructure. How does it matter? Thank you very much. And I just cancel it. Thank you for, if you have any question, you can ask me through the email or attend my